Let's finish the review of calculus. So, recall the fundamental theorem of calculus, namely that if you want to compute an definite integral, all you have to do is you have to find a function big F whose derivative is equal to the function that you were given, and then plug in the upper and lower limits and take their difference. So the fundamental theorem of calculus basically tells us that integration is the same as antidifferentiation, which is exactly what I say here. So with the fundamental theorem in mind, we make the following definition. An indefinite integral, so it's the same notation, but just without the lower and upper limits. An indefinite integral is any function that satisfies the following relation. So if the indefinite integral is big F, then that is the same as saying that little f is the derivative of big F, right? The function big F is called an antiderivative, and the process of finding big F is called either antidifferentiation or integration. So here is a table of common indefinite integrals for reference. And yeah, most of these, because we're doing differentiation in reverse, we can take all of the differentiation formulas that we already have and just reverse them. That's what most of these formulas are, ultimately. So here we are noting that if you have a constant, you can pull it out of the integral. That's important to remember because we're going to be doing that all the time. Integration distributes over addition. So the antiderivative of a constant is just a constant times the variable, and so on and so on. This is the power rule. If you have a power function, just add 1 to the exponent and then divide by that. So that's the reverse of the power rule for ordinary derivatives. And then here are a bunch of trig functions. And these are all literally just doing the derivative rule in reverse. So like the derivative of sine is cosine, so that means the integral of cosine is sine, and so on and so on. So why do we add a plus c at the end of an antiderivative? So it's a formality, but really the reason that we're doing it is because we want the indefinite integral to be as general as possible. So remember what the indefinite integral is actually doing. It's an antiderivative. It is some function, any function, whose derivative equals the thing that we were given. Now here's the thing. There are infinitely many antiderivatives for a given function. Like, for example, say that this was sine x plus 0. I differentiate that, I get cosine. Say this is sine x plus 5. Differentiate that, I get cosine. Sine x plus literally any number. I differentiate this, and the constant just disappears, because the derivative of a constant is 0. So, so all of the antiderivatives vary up to a constant. So really, the antiderivative of a function isn't a single function, it's a whole family of functions. It's an infinitely large family of functions where they are all distinguished from each other by the presence of some offset. And that's basically what I say here. As it happens, and you can prove this pretty simply, but I'm not going to do it, that given a function f, there are infinitely many antiderivatives, but they all differ by a constant. So if, say, big F and big G are both antiderivatives of f, then that means that big F and big G are the same, just up to some offset. So adding this plus c ensures that we are capturing all possible antiderivatives of the function that we were given. And yes, it is a formality, but, you know. Okay, so let's antidifferentiate this dude. So first off, I notice that we have a subtraction here, and we have a couple constants. So let's start by breaking this up a little bit. Okay? So this constant 10, so you can pull that out. minus 2 integral secant squared x dx, right? So that's using property 1 and property 2, respectively. Now, what's the antiderivative of x to the fourth? Well, that's just going to be the power rule. So add 1 to the exponent and then divide by it. So there's that 10 still hanging out there. So x to the power 5 over 5 minus 2. Now, what is the antiderivative of secant squared? Well, antiderivative of secant squared is tangent. And then we're done, so we add in the plus c. And we may as well clean this up a little bit. I mean, here we have 10 divided by 5. Well, 10 divided by 5 is 2. So there we go. So that's a little bit better, a little bit easier to look at. Let's see. Evaluate cosine theta over sine squared. Well, what can we possibly do with this guy? So, on the website Paul's Math Notes, Paul's online math notes, which I posted a link to in the first announcement, you can download a cheat sheet, a trigonometry cheat sheet, that has all of the trigonometric identities that you will be likely to need. So, one trig identity that you may or may not remember well, there's two of them. Recall, cosine theta over sine theta. There we go. Cosine theta over sine theta, that is cotangent. That is literally what the cotangent function is. It's just cosine over sine. Similarly, 1 over sine theta is equal to cosecant theta. Again, that is literally the definition of the cosecant function. So why do I bring those two identities up? Well, because that's exactly what we have here. We have cosine over sine times 1 over sine. If we just, split this up, split the sine squared into its two factors. Oops. Excuse me. There we go. Right? Just split that up, split up the bottom. So that is the integral of cotangent times cosecant So integral of cotangent cosecant, and well, what do you know? We have a formula for that as well. So integral of cosecant cotangent is negative cosecant. And there we go, and we're done. I suppose I should put little equals here. There we go. Okay, evaluate this dude. Well, once again, we can split it up a little bit. Notice also that this is a definite integral now. So before we're finished, we're going to have to evaluate the antiderivative at the endpoints. And I need to put a dx here as well. Don't forget to do your proper notation with the integral sign and the dx. So I pulled out the -6, of course, because that's constant. Okay, so power rule. X to the third becomes x to the fourth over 4 minus 6. And then x, well, this is the same as x to the power 1, so this becomes x squared over 2. Now, I'm not going to add the plus c, because we still have to evaluate this between 0 and 3. And even though I separated them like this, when you're doing the final part of like plugging in the endpoints, you can do it on the entire thing, right? You don't need to do it on each of these guys separately. You'll end up getting the same result regardless. So we still have to evaluate that between 3 and 0. Okay. So let's see. If we plug in 3, what do we get? Well, all right. At this point, it's just rote computation, so there's really not much to say. 6 divided by 2 is 3. 3 squared over 2. So that's one big chunk. Minus. And then what do we get when we plug in 0? Oh, hey, so what do we get when we plug in 0? Well, 0 to the 4th over 4 is 0. 0 squared over 2 is 0. Times 6 is still 0. So hey, luckily for us, that whole second bit just disappears entirely. So that's convenient. And then finally, we just crunch the numbers. This becomes, let's see, denominator is going to be 4. Numerator is going to be 3 to the 4th minus 3 cubed times 2. So that is all. So now I'm just throwing this into my calculator because I can't be bothered. Okay, so that's 27 over 4. Yep. So, easy. Just power rule. What is going on here? So I'm going to skip the step where we split this into 2 pieces and just go straight to doing the antidifferentiation, because these 2 guys are simple standard forms. So x, well, this is the same as x to the power 1. So power rule, that becomes x squared over 2. Minus 12, because you could pull, you can just pull constants out. So the antiderivative just ignores the fact that there's a 12 there. And then what's the antiderivative of sine? Well, let's see. It's minus cosine. So we have, notice I'm being careful to place parentheses there because now we have 2 minuses right next to each other. So we're going to have to deal with that. Okay. And now, once again, it's just rote computation. So if you plug in 12, we get 12 squared over 2. Well, that's the same as 6 squared, so that's 36. Plus, because of minus and minus becomes plus, 12 cosine of 12, whatever that is. I don't know what the cosine of 12 is. It's some crazy number. Minus, so what happens when we plug in 0? Well, 0 squared over 0 becomes 0. Cosine at 0 is 1. The cosine at 0 is 1. So if this is the first chunk, what you get when plugging in 12, what is the second chunk? Well, that is 0 plus 12 cosine of 0. Right? I guess I don't need these extra parentheses. And so finally, cosine of 0 is 1. So we get 36 minus 12, which is 24. So our final answer is 24 plus 12 cosine of 12. And then you can throw this into a calculator if you want, figure out what it is, but I don't really care. It's around 0.84, if you're interested. I prefer to keep my answers exact whenever possible. Now, what's going on here? Well, this thing may look intimidating at first, but really all we need to do here is power rule. So, you may remember from algebra that if you have a gigantic fraction like this, but the denominator is only one term, then in fact, all we're doing is we're just dividing each of these individual things by t squared. So really all we have here is 2t squared over t squared plus t squared root t over t squared minus 1 over t squared dt. Right? That's really all that we have. Now, well, we can clean this up a little bit. And in particular, if we want to apply the power rule, then we're going to want to make everything look like this, right? We're going to want to express it as variable to an exponent. So let's see what we end up with. So first off, t squared over t squared, well, that just cancels, so we end up with 2. Similarly, t squared over t squared, that cancels, so we just have root t left over. And recall, root t is the same as t to the power 1/2. 1 over t squared, that's the same as t to the power -2. Okay? So that's what we've got so far. And we've written it in a way that is amenable to the power rule, right? Because now all we need to do is just add 1 to the exponent and then divide by, well, whatever we end up with. So antiderivative of 2 is 2t. You just plop the variable next to it. Let's see, 1/2 plus 1 is 3/2, and then you divide by 3/2. But here's the thing. Dividing by 3/2 is the same as multiplying by 2/3. So, you know, I think I would rather do that instead. Right? Dividing by 3/2 is the same as multiplying by 2/3. As for this guy, well, let's see. -2 plus 1 is -1, and then I divide by -1 as well. But if you're dividing by -1, I've got this negative out here, so that's just going to cancel it. That's just going to cancel the sign. And then we still have to evaluate. So at this point, it all just becomes rote computation. So I will save you the trouble and just do the computation myself on my calculator here. And just make sure that you can actually reproduce this on your own, right? Make sure that you can actually get the same number. So let's see. You know what, though? Okay, yeah, no problem. I was a little bit worried about the 3/2. I thought that, well, you know, maybe we're just going to have to do it by hand anyway because there's going to be like a radical in it. But no, luckily enough, it all just reduces to a fraction. So that's neat. Okay. So what we've done here pretty much covers these are all cases where you can look up the antiderivative directly in this table. And then, you know, you split it up according to addition, maybe you pull a constant out, but ultimately all we're doing is just using this table to find the antiderivatives directly. Naturally, if that was our only strategy, then that's not going to take us very far. So, what I want to talk about in the rest of this part of the lecture is what's called integration by substitution. So this is going to be an integration technique that is very, very, very useful, and it's going to be pretty much ubiquitous throughout this course, right? We're going to be using it a lot. And you can derive it, like ultimately this method is based on the chain rule. And you can derive it if you want. I don't think the derivation is terribly interesting or enlightening. You can look it up if you're really interested in rigorously seeing why this works, but I think it's better to just do it and see what happens. The general idea here is that you've been given something that looks very complicated, right? It's something that doesn't immediately fit into one of the rules up above, like one of the things in the table. So instead, what you can do is you can introduce a new variable, which we are just by convention going to call u, but you can call it anything you want. And then the hope is that once you have rewritten this integral to be entirely in terms of the new variable u, it ends up being something which is in that table above. It ends up being something that we actually know how to do, as opposed to what we have right now, which is kind of a mess. So let's define a new variable u, and, well, let's call u x to the fourth plus 2. Let's call it this big chunk inside the parentheses. Well, if u is defined to be x to the fourth plus 2, well, then what can we say about u? Well, one thing that we can certainly say is we can take its derivative. So du dx, which is a notation that we use for the derivative of u with respect to x. Well, let's see, power rule. So that becomes 4x to the third, and the derivative of 2 is 0, so that's it. Now I'm going to do something that seems strange, but trust me, it actually works. Everything actually all fits together. I'm going to rewrite this equation a little bit. Now, this dude here on the left, this is not actually a fraction. This is just a symbol. But the magic of the integral notation and the magic of this technique is that, as it happens, we can behave as if this du and this dx are not merely symbols, but are actually variables in their own right. Like going back to the physical interpretation of the integral that I was talking about in the previous section, you can think about dx as being just like a really, 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 really thin slice of an interval. Similarly, du would be a really, really, really thin slice of the u-axis, whatever that is. So we can imagine, even though it's not strictly true, we can imagine that these d terms are in fact numbers, and perform algebra with them as such. And miraculously, it all actually works. It all fits together. So all I did here is I just multiplied both sides by dx, get dx over here. And then I'm going to solve for dx in the equation above. So if we solve for dx, well, we're just dividing both sides by 4x cubed. Like so. Okay, now why did I do that? Because now I'm going to take this expression for dx and I'm going to plug it in here in the integral. So I'm going to plug our information into the integral. So let's see what we have. We've got an x cubed. All right, that's still there. Oops. We've got cosine x to the fourth plus 2. Now x to the fourth plus 2, we already gave that a name. We said that that was going to be u, right? So x to the fourth plus 2, that all just becomes u. dx. Well, dx is all of this stuff. Right? So this is what our integral looks like now that it has been transformed. As it is, though, this doesn't make any sense. I mean, the variable over here in the d term, that's the variable that we are anti-differentiating with respect to. So now that we have a du over here, we want to anti-differentiate this thing with respect to u. But the problem is this guy isn't a function of u. It's not a function of u, it's a function of x and u. So in order for this to work, we need all of the x's inside here to go away somehow. And luckily for us, these x cubes just cancel out. So it's not a problem. Right? We've got an x cube on top, an x cube on bottom, they cancel out. So what do we end up with? Well, we have 1/4, so may as well pull that out, because that's a constant. The x cubes cancel. And then all that we have left is just cosine u du. So by introducing this new variable u, and then doing this magic symbol manipulation of, saying that dx is equal to whatever times du, we have actually obtained an integral which has only u's in it, no more x's. So what is the antiderivative of cosine? Well, we know what that is. We have a formula for that. The antiderivative of cosine is just sine. So at this point, this dude is super easy to figure out. It's just sine. And then this is an indefinite integral, so we have to add in the plus c. Now, before we end, since the original problem was in terms of x's, we want the final answer to be in terms of x's as well. So let's just replace u with its original definition, which was x to the 4th plus 2. So okay, 1/4 sine x to the 4th, I'm sorry, it was plus 2, plus c. And that's it. And then if you want, you can verify that if you differentiate this guy, well, you're going to have to use the chain rule because we've got a function that's embedded inside of another function. But verify for yourself that if you differentiate this guy, indeed, you do end up with x cubed cosine x to the 4th plus 2, which is exactly what you wanted, since we're looking for an antiderivative. So, similar situation here. We know how to deal with a square root. I mean, the square root is just a power of 1/2, so we can do the power rule. The problem is that we've got all of this junk underneath it. This plus is particularly problematic. So let's introduce a new variable. And just like we did before, if we've got like a big chunk of stuff inside parentheses or a big chunk of stuff inside a box or, with some delimiters around it, it's a good first guess to just let u be whatever that is. So let u be whatever is inside the parentheses or whatever is underneath the square root. And typically for the sort of problems that you're likely to see, that's what the author was intending, so it's going to end up working out. So let u equal 2x plus 1. What do we want to do next? Well, we want to differentiate so that we can solve for dx, right? We got to get that dx out of there. That's what we really need, because we can't integrate with respect to the new variable until this dx has somehow been replaced with a du. So what's the derivative of this? It's just 2. Okay. So if we solve for dx, we get 1/2 du, right? Literally just move the dx up here, move the 2 down here. So let's plug this data into the original integral. And what do we have? So we've got integral square root of u, right? 2x plus 1 is all just u now. And then dx has been replaced with 1/2 du. And in fact, this 1/2, let's just go ahead and pull it out, because that's a fraction, or it's a constant. So now, all we need to do is take the antiderivative of the square root. So what's the square root? Well, we did it a little bit before. It's u to the power 1/2. So that's just power rule again. Let's see. So we end up with u to the 1/2 plus 1 is u to the 3/2. Dividing by 3/2 is the same as multiplying by 2 over 3, like so, plus c. And then let's clean this up a little bit, because these 2's cancel out to leave us with just 1/3. U, well, we want to write everything in terms of x's again, so u was 2x plus 1. That's all to the 3/2. Ugh. And then plus c at the end. Yep, so that's all that we need to do. All right. Well, same story here. I mean, we've converged on a pretty solid strategy for dealing with these guys, which is just let u be whatever was inside the parentheses, or in this case, whatever is underneath the square root. Now, differentiate. Let's see, 1 goes away. Bring down the 2 to get -8. 2 minus 1 is just 1, so -8x. Solve for dx, so that just becomes -1 over 8x du, right? Just move the dx up here and move all this stuff down here. And now plug it into the integral. And let's just see what happens. So on the top, we still have x, and on the bottom, we have square root of 1 minus 4x squared. Well, that all just became u. What about dx? Well, dx is all of this stuff. Oops. And got to be careful here. We are multiplying by that -1. We are not subtracting. In fact, I mean, since ultimately we're all just multiplying this by this -1/8, let's just go ahead and pull that out. Right? I always like to pull out the fractions at the earliest opportunity. That's always going to make things a lot easier to look at. So these x's cancel out, and we are left once again with an integral that has only u's in it, which is exactly what we want. So we are left with integral of 1 over square root u. Well, we're going to do the power rule, so let's go ahead and write that as u to the power -1/2 instead, right? The 1/2 comes from the square root. The negative comes from the fact that it's a reciprocal. It's in the denominator. Yeah, and we're almost done. Now we just got to do the power rule. So let's see. So what's negative 1/2 plus 1? Well, negative 1/2 plus 1 is positive 1/2. Then we have to divide by 1/2, but dividing by 1/2 is the same as multiplying by 2. So, got that. And finally, let's just clean it up. So 2 divided by 8 is 1/4. Replace u with what it originally was, so 1 minus 4x squared. And that's all to the power 1/2. If you don't like the power 1/2, you could write square root instead. It doesn't make any difference to me. Sometimes I prefer square roots. For the most part, though, I think fractional exponents are going to be better. So it's really just a matter of preference. Okay, let's keep going. So let u be whatever is inside the parentheses. That is a strategy. I'm not going to say that that's always going to work, but for the exercises that you're likely to see, if you just let u be whatever is inside the box, so to speak, then usually that's going to work out. Oh no. Okay. Differentiate. So the derivative of this guy is just 5. Solve. So dx is equal to 1/5 du. And then plug in. So our integral becomes the integral of cosine 5x. Well, 5x is now being replaced with u. And dx has now been replaced with 1/5 du. So let's put that in there. And once again, this 1/5, let's put it out front. Okay. So what's the antiderivative of cosine? Well, that's just sine. And let's go ahead and save some time. This is going to be the sine of u. What is u, though? Well, u is 5x. So there we go. That's all there is to it. Now, before we move on, I want to mention something. I want to mention something really that you should keep in memory. So, integrals of this form are going to come up a lot in this class, especially later when we start. Especially later when we start doing trigonometric integrals. So integrals with more, trig in them. So I just want to say this once and for all. If you encounter an integral which is like this, it's trig function with some number inside here, just memorize the following formula. So integral, actually let me make it a big integral. So the integral of sine ax, where a is just any number, is equal to 1 over a, and then whatever the antiderivative of sine is. So the antiderivative of sine is minus cosine. So, like so. I think this is just something that's worth remembering. So sine ax, antiderivative of sine is minus cosine, but the presence of this additional number in here just means that we need to divide by it. And similarly, a similar thing happens in the case of the cosine. So integral cosine ax dx is equal to 1 over a sine ax. So it's this latter form that we just computed where a is equal to 5. So these two facts I think are worth remembering because they are going to come up somewhat often. And if you don't just remember these, then you're going to have to do a u substitution every single time. And then that's just a waste of time ultimately. Alrighty. So this one is interesting. I like this one because it sort of throws a curveball your way. So let's start the way that we've been starting. Let u be whatever is inside the box. In this case, it's square root rather than parentheses. Let's differentiate. So the derivative of this is 2x. Solve. So dx is equal to 1 over 2x du. And now let's plug these things into the integral to see what happens. So we've got x to the power 5, square root of u, and then instead of dx, we have all of this stuff. Well, we can clean this up a little bit. I mean, we've got a 1/2, so let's go ahead and pull that out. We've got an x to the power 5 on top, and x on bottom, so one of those x's cancels, and we get x to the power 4. We know how to deal with square root of u. But we appear, at least momentarily, to have run into a roadblock. Because we need, if we're going to integrate this guy with respect to u, then we need this to be a function of u. But it's not. It's a function of u and x. Well, that's a problem. We need this x to go away somehow. So we need that x to go away. Well, what can we possibly do to deal with that? I mean, it's not going to cancel out. So how about this? Up here, we started by saying that u is equal to 1 plus x squared. Well, let's solve for x in this equation. Right? Because then we'll have x in terms of u. Like, why not? So, what am I doing? I'm sorry. So, yeah. So if you solve for x in this equation here, x is equal to square root u minus 1. And in fact, because square roots make me a little bit nauseous, because square roots always, you sort of have to worry about domain, because you can't take the square root of a negative number, and the domain of these guys hasn't been specified at all. Just to make myself feel a little better, instead I'm going to say, I'm going to solve not for x, I'm going to solve for x squared. I mean, it's not going to matter in the end, as we shall see shortly. Indeed, here we have x to the power 4. Well, x to the power 4 is just x squared squared. So x squared squared is going to be this squared. So our integral becomes, so x to the power 4 has become u minus 1 squared, and then we still have that square root u hanging out. Okay, so we have successfully written an integral which is identical to the one that we started with, but instead of x's, it now has only u's in it. So at this point, we can actually do something. So let's expand this out and then hit it with the power rule. So if we expand this, we get u squared minus 2u plus 1. Please don't forget that middle bit. Make sure you FOIL this correctly. Oops. Right? And then let's take this 1/2 and distribute it. So because 1/2 is just u to the power, or I'm sorry, because square root is just u to the power 1/2, all we're doing is we're just going to increment the exponents by 1/2. So u squared times square root of u becomes u to the power of 2 plus 1/2. 2 plus 1/2 is 5/2. This is u to the power 1. 1 plus 1/2 is 3/2. And then square root of u times 1, well, that's just 1 to the... Yeah, there's no change there. And now we hit it with the power rule, and we are done. So let's see. So 5/2 plus 1 is 7/2. Dividing by 7/2 is the same as multiplying by 2/7. Three halves plus 1 is 5/2. Dividing by 5/2 is the same as multiplying by 2/5. And let's go ahead and clean that up. That becomes 4/5. See, the good thing about doing this all and you're typing it out instead of on a whiteboard is you can do little corrections like that immediately without wasting extra ink, although you do waste extra time in explaining it. Or at least I do. So 1/2 plus 1 becomes 3/2. Divide by that, 2/3. Plus c. Oh, whoops, this integral shouldn't be here anymore because I'm integrating. Now all of this is being multiplied by 1/2. So let's go ahead and bring that through. So let's see. If we multiply this by 1/2, the 2 goes away. Multiply this by 1/2, 4 becomes 2. Multiply this by 1/2, 2 goes away. So there's that taken care of. And then finally, just replace u with 1 plus x squared, and we will be done. Actually, you know what? Let me just take this guy, copy paste it. You can also copy paste in this sort of environment, which is cool. Uh-oh. Except I may have screwed myself over. Okay, no, we're good. Are we? Are we good? I don't think we're good. I think I've confused. I think I've confused the system. Whatever. I hope that I can also show you guys that typing math isn't necessarily hard. There are a few shortcuts that you need to use, but if you use this program that I'm using, which is called Lyx, L-Y-X, it's not very easy to set up, but once you have it set up, typing out math is really pretty easy. So for your future scientific careers, it may be worth learning how to type math. Alrighty, evaluate this. Yeah, do we really need to? I mean, we already did square root 2x plus 1. That was up here. Yeah, so that was this. So all that we would be doing is just, right, the only difference is that now this is a definite integral, so we would just be plugging in the top and the bottom and then subtracting them. Boring. Also, we've almost hit the 50-minute mark. So let me just do this one quickly, and then that'll be it for this particular video. Okay, so same strategy as before. Let u equal 3 minus 5x. So derivative of that is minus 5. Solving for dx, we get minus 1/5 du. So one thing that's different here is that because this is a definite integral, it begs the question, how does making this change in variable affect definite integrals? So when we change variables in a definite integral, we change the bounds of integration, or I'm sorry, the limits of integration as well. So the first limit of integration is x equals 1. So x equals 1 becomes, well, let's see. When x is equal to 1, u is equal to 3 minus 5 times 1, right? Which is equal to 3 minus 5, so negative 2. So this lower bound transforms from 1 into negative 2. Similarly, the upper bound of x equals 2, that transforms into, well, u equals 3 minus 5 times 2. So that's 3 minus 10, which is negative 7. So then when you're plugging everything into the integral, make sure you include the new bounds. So the new bounds are now from negative 7, or I'm sorry, from negative 2 to negative 7. Yeah, because they have to correspond. What else do we have? So we have, so sometimes it's a convention to put the dx on top here. I'd rather keep it over to the side. So let's see, 1 over u squared. So that's 1 over u squared dx, and then dx is just minus 1/5 du. So all we're going to do is pull that minus 1/5 out front. So there's that. This is just the power rule, because this is u to the power negative 2. So that's easy enough. So u to the power negative 2. So add 1 to the exponent, we get negative 1. Divide by negative 1, and that flips the sign. And then this still has to be evaluated between negative 2 and 7. Negative 7. So let's see. We just got 1/5. This is the same as 1 over u. So we can just plug in the bounds directly now. There's no need to transform back to x. That's really the takeaway from this particular example. Like so. And if you simplify that, what does that come out to? Let me see. I don't want to do it by hand, so I'm just going to do it in my calculator. 9 over 70. Neat. I think. Wait, no, it's not. That's the wrong sign. I'm sorry. I'm sorry, it's 1/14. So let that be a lesson to you. Be very careful when you're doing, see, the problem was I omitted the negative sign when I was doing the calculation. So be aware of that. That's a very common mistake. Okay, signing off for now.